In this video, we're going to explore Lewis symbols and Lewis dot structures. Lewis symbols show us how many electrons are in the valence shell of individual atoms. Lewis structures begin to show us how exactly the electrons in the valence shells are forming our covalent bonds in a molecule. Let's look at some of the basics. When we're writing the Lewis symbol of an element, we begin by just writing out the atomic symbol of the element, in this case generic element X. This would represent the nucleus of the element along with all of the core electrons. We then look at 4 different regions around the element as areas where electrons would go. And so we would start to fill in those boxes to account for any of our valence electrons. For instance, if there is only one valence electron, then we simply write 1 dot. 2 valence electrons will be 2 dots, 3 valence electrons, 3 dots, and so on. Note that for the Lewis symbols of individual atoms, the placement of this dot is arbitrary. You can write it on any side of the element that you want. And so here we see the Lewis dot symbols for some of the main group elements. What we begin to notice immediately is that the elements that are in the same groups, group 1 here, lithium and sodium, have the same number of electrons in their valence shell, and so they receive equivalent Lewis dot symbols. Group 2, beryllium and magnesium, group 3, boron and aluminum, and so on, all the way out to the noble gases, which have a full 8 electrons in their outer valence shell. And so again, we can relate our electron configurations to our Lewis structure. We see here the electron configuration of carbon, and we have our electrons in the valence shell right here. So that's 4 electrons in our valence shell. And so we get 1, 2, 3, 4 electrons in our Lewis symbol. As we move on to looking at the Lewis dot structures of full molecules, we have to keep in mind what we call the octet rule. The octet rule tells us that atoms will share electrons in such a way that they will fill their outer valence shell. And so let's look at the simplest example of hydrogen. Here we have one hydrogen atom with its 1 valence electron. Hydrogen is in the first period, so it only has 1 Bohr shell, meaning we can fit 2 electrons total in that outer shell. And so in order to form an H2 molecule, 1 hydrogen donates 1 electron, 1 hydrogen donates another electron, and now both hydrogen atoms have full outer shells. They both have 2 electrons in their outer shell, making it a stable, neutral compound. We can represent that bond that is formed now either as these 2 electrons, or we can also represent it as a line. This line is 1 covalent bond made up of 2 different electrons. Here, we're going to look at the compound that will form between hydrogen and fluorine. We have our hydrogen atom here with its 1 valence electron. We have our neutral fluorine atom with its 1, 2, 3, 4, 5, 6, 7 valence electrons. And so when they come together to form hydrogen fluoride, hydrogen brings along its valence electron, adds it to fluorine's valence electrons, and we get this chemical bond, this covalent bond between the 2. And so now, once again, hydrogen has a full outer shell. It's got its 2 electrons that it wants. Fluorine can fit 8 electrons in its outer shell, and by sharing with hydrogen, that's now what it has. And so we say that both atoms now have an octet. Just keep in mind that an octet for hydrogen really means 2. but fluorine has its octet here. And so we have in hydrogen fluoride what we call one bonding pair, forming the bond between the two, which we can represent as a line. We also have 1, 2, 3 lone pairs in the molecule. Lone pairs are electrons that are around an atom but are not participating in bonding. And so we have 3 lone pairs around our fluorine atom. When putting together Lewis structures for a compound, it's helpful for us to keep in mind what we call the covalency of atoms. The covalency is the number of bonds that an atom will typically form. And so, for instance, hydrogen has 1 valence electron, so it will only ever form 1 bond in order to fill its outer shell. Chlorine has a valence of 7. We have 7 valence electrons. And so it would want 1 electron from other atoms in order to form its octet. So it will typically form 1 bond. Oxygen has 6 valence electrons. So in order to fill its octet, it would want 2 electrons from other atoms, and so typically form 2 bonds, and so on. Nitrogen would typically form 3, and carbon would typically form 4. Now remember, the number of valence electrons is the same as you move down a group in the periodic table, and so this pattern would hold true for all of the other elements in these atoms' groups. We have to keep in mind that this is a general rule of thumb for these elements, though. We'll find that in some cases, some of these atoms can form more or less than what the covalency would imply. But these will be rare instances which we will discuss at a later time. And so a Lewis structure is a representation of a molecule showing all of the electrons, both bonding and non-bonding. And so here we have H2 with the 2 electrons in the bond. Here we have Cl2 with our 2 electrons in the bond, and each chlorine atom also has 3 lone pairs around it, 3 non-bonding pairs of electrons. And so here's a list of rules that we're going to use when we write Lewis structures of compounds. The first thing that you want to do is to calculate the total number of valence electrons for all atoms in the compound. If you have anions, you then add electrons for your amount of negative charge. For cations, subtract electrons for your amount of positive charge. You then write out the skeleton structure of the compound. Generally speaking, the least electronegative atom will be in the center. Hydrogen and fluorine will always occupy the terminal positions, meaning they will never be in the middle. After writing your skeleton structure, we place 1 pair of electrons between all of the bonded atoms. So we form a bond with 2 electrons between all of the atoms that want bonds. We then complete octets of the outer atoms by adding electron pairs. Whatever we have remaining for electrons, we then place as lone pairs on our central atom. If any of the atoms at that point do not have an octet, we will then form double or triple bonds as needed, and we'll talk about what that looks like. Hydrogen atoms will never ever have lone pairs or multiple bonds. When you're writing Lewis structures, hydrogen atoms will only ever have 1 bond. Say that out loud. Hydrogen atoms will only ever have 1 bond. Now this seems like a lot of rules to keep in mind, but if you stick to 2 main overarching rules for Lewis structures, 1, use all electrons, and 2, every atom gets an octet. If you go by those 2 rules and make sure that those 2 rules are always satisfied when writing a Lewis structure, you will probably be okay. And we'll look at some examples of what that means. And so here we're going to write the Lewis structure of PCl3, phosphorus trichloride. So the first thing we want to do is find out how many electrons we have to deal with. Phosphorus has 5 valence electrons. Chlorine has 7, and we have 3 chlorine atoms total. 3 times 7 is 21, plus our 5 from phosphorus. Means that we have 26 total electrons to deal with for phosphorus trichloride. Our next step is to place our least electronegative atom in the center, as long as that is not hydrogen, because remember, hydrogen always goes on the outside. But in this case, phosphorus is less electronegative, and so it's going to go in the middle, and we're going to place our 3 chlorine atoms arranged on the outside. We then connect all of those atoms with single bonds. Remember that those single bonds each represent 2 electrons. And so we've now used 2, 4, 6 electrons total, meaning we have 20 electrons that we still need to place around this compound. And so our next step is to fill all of the outer atoms with their octets. And so we're going to place 3 lone pairs around each chlorine so that each chlorine atom now has an octet. So we just put 6 electrons around each chlorine. We have 3 chlorines. So we've just placed another 18 electrons. This leaves us with 2 electrons still to place around the molecule. Now that the octets of all the outer atoms are full, we can place those 2 remaining electrons on our central atom. And so now, let's see if our 2 overriding rules have been met. First, we have to use all electrons. We said that we had 26 electrons to work with, and so let's see if we've used them all. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So all of our electrons have been used. Now let's check for octets around each of our atoms. 8 electrons around chlorine, 8 electrons around phosphorus, 8 electrons around this chlorine, and 8 electrons around this chlorine. And so we have used all of our electrons. Every atom has an octet. So we would say that this is a valid Lewis structure. Now let's say we run out of electrons before we have an octet around each of our atoms. And so in this case, we're looking at hydrogen cyanide. And so when we were constructing the Lewis structure of this, hydrogen had its 1 electron, carbon had 4, nitrogen had 5, and so a total of 10 valence electrons. And so we have in fact used 2, 4, 6, 8, 10. So we have used all of our valence electrons. We do have an octet around hydrogen. It has 2 electrons. We have an octet around nitrogen, 2, 4, 6, 8. However, carbon only has 2, 4. Carbon does not have an octet. And so what we can do then is transfer 2 of the pairs around nitrogen and put those into bonds as well. And so instead of being a non-bonding pair, this pair of electrons is now going to form an additional bond between carbon and nitrogen, and so is this pair will form an additional bond. And so what we have is what we call a triple bond between carbon and nitrogen. Rather than just one bond connecting the two, we have 6 electrons forming 3 separate bonds between carbon and nitrogen. And so now let's check our 2 rules. 2, 4, 6, 8, 10 electrons, so we've used all of our electrons. Hydrogen has 2 electrons around it, so it has its octet. Carbon has 2, 4, 6, 8 electrons around it for an octet. Nitrogen also has 2, 4, 6, 8 electrons for an octet. And so we've used all electrons, and we have octets around all atoms. This is now a valid Lewis structure. And so let's look at another example. Here we have carbon dioxide. Carbon's going to be our central atom. We have 16 valence electrons to work with. And so we're going to place carbon in the middle, our 2 oxygens on the outside, connected with single bonds. So now we've used 2, 4 electrons. And so now we're going to place electrons around our outer atoms first. 2, 4, 6 to give this oxygen an octet. 2, 4, 6 to give this oxygen an octet. So we have now used all of our electrons. 2, 4, 6, 8, 10, 12, 14, 16. Both oxygens have octets, but carbon does not. And so we're going to take a lone pair from each oxygen atom and use that to form an additional bond between carbon and oxygen, leading to the formation of a double bond between oxygen and carbon on each side. So a double bond here, a double bond here. We now have 2, 4, 6, 8, 10, 12, 14, 16. So we haven't added or taken away any electrons. We've just moved some. And now every atom has 8 electrons around it. So every atom has an octet. We've used all of our electrons. This is a valid Lewis structure. Another example, formaldehyde. CH2O. So we have 12 valence electrons total. Remember, carbon is less electronegative, so that's going to go in the middle. Hydrogen can only ever form one bond. And so we'll have this for our skeletal structure. We're going to connect every atom with single bonds. We now have 6 remaining electrons. We're going to place those 6 around oxygen. And now we've used all electrons. 2, 4, 6, 8, 10, 12. Hydrogen has an octet with its 2 electrons. Oxygen has an octet, 2, 4, 6, 8. Carbon, however, only has 6. And so we're going to take 2 of the electrons that are currently on oxygen, and we're going to place those into a bond instead. So now every atom has an octet, and we've used all of our electrons. Remember that these are the 2 primary rules when you are forming Lewis structures. Use all electrons, and every atom receives an octet. In the next few slides, we have several examples. And so stop the video now, write the Lewis structure for silicon dioxide, restart the video to check your answer. So stop the video now. And now here we have the Lewis structure for silicon dioxide. And so once again, just check to be sure that all electrons are used and that every atom has an octet. Stop the video to write the Lewis structure for CH4, methane. And now check your answer. Another example, here we have IBr2+. Remember, you have to adjust your electron count to account for any charges. Here we have a charge of 1+, and so you will need to subtract an electron from your atomic electron count. Stop the video now, write the Lewis structure, and then restart the video to check your answer. And here we have our Lewis structure for IBr2+. And so in this video, we've discussed the basics of writing Lewis structures. There are lots of different practice opportunities on both my website and just online in general. If you simply Google Lewis structure practice, you will find lots and lots of different practice opportunities for writing Lewis structures. Do not skip steps. If you go very systematically and write out the Lewis structures given the steps we've outlined on this video, you will get the right structures. As anything, the more and more that you do, the more comfortable you will get, the better you will get at writing these, and you'll start to notice patterns that will help you speed up. But remember the two overarching rules. Use all of your electrons, and every atom gets an octet. I hope this video has been helpful. Be sure to come see me or get some extra help if you are still having troubles with Lewis structures. This will be a very important skill for us moving on to the very next topic.